I'm going to use this chart and this set of data to try to explain the concept of simple linear regression. The chart is essentially the graph shown in figure 11.4, and the data are the data shown in figure 11.5, which are the data that make up the chart. Length of stay is the variable that appears on the horizontal axis, and total charges for the stay is the variable that appears on the vertical axis. Within the concept of simple linear regression, we are trying to see if we can predict total charges, the y variable, using length of stay. The blue dots in the chart represent the combination of length of stay and charges, so that, for example, this blue dot, as the title shows, is a stay of 10 days that cost $8,769. The other blue dots are similar. The red line represents the mean value for total charges, which appears here, but also appears here. The line itself is going to be the line which we will try to fit to the blue dots. Right now the line is horizontal. It has no slope, and its intercept is the mean. We are going to change the slope of the line, which will also change the intercept, and we're going to try, by changing the slope of the line, to fit the red line to the blue dots. The line is defined by the formula on page 338, 11.2a. 11.2a says that the predicted value of y is equal to b1, which is the slope, times the value of x, which is length of stay, plus the intercept. As we move the slope, the intercept will change to try to fit the line to the blue points, with the mean value for points on the line always being the same as the mean value for total charges. Now, because the total charges increase as length of stay increases, the slope of the line will be positive. The slope actually represents the increase in cost per day for each additional day of stay. So let's imagine what the increase in cost per day might be on the basis of the data we see here. The cost for 10 days of stay is almost $9,000, and the cost for 1 day of stay ranges between something less than $1,000 and something more than $3,000. So let's imagine that the cost per day may be increasing at about $500. We'll change the slope to 500. Now the intercept has changed to 2020, and we can see that the line appears to better fit the data, but we might be able to do better. Let's try 600. Now the intercept has been reduced, and the line appears an even better fit. Let's try 700. The line appears to be even a better fit to the data. Let's try 800. In general, I would say that's a fairly good fit to the blue dots with a slope of $800. Okay, if we accept 800, what we're saying is that the cost per day predicted for any stay is $800 times the number of days of stay plus a flat $1,075. What regression attempts to do is to find this line through the data, and the line is defined in a very specific way. That is, it is the line that minimizes the sum of squared differences between the blue dots, that is, the points representing the data, and their vertical projection on the red line. To see what that means, let's go back to a slope of 0. Now, if we look at this blue dot at 87.69 and the red line here, the red line is at 35.95. There's a difference of approximately $5,000 between this blue dot and this red line. If we square that difference of $5,000, that will add $2,500,000 to the error sums of squares. The error sums of squares is seen here. That is the sum of all the differences between each blue dot and its projection on the red line. What we are trying to do in regression is to minimize that sum of squared errors. In other words, we're trying to find the line that makes this value as small as possible. If we look at this value here, 7.85 e to the plus 07 is a very large number. It is actually 78,500,000. What happens when we move the red line? Let's go back and move it to 500. This is obviously not a good fit, but we've reduced the sum of the squared errors to 26,100,000. Now if we increase this to the 800, which we felt was a good fit, we can see that we've reduced the sum of the squared errors to 17,400,000, or 1.7 e to the plus 07. Let's look at 900 and see if it improves our sum of squared error. Now we can see that by going to 900, the sum of the squared errors has gone back up to 1.8. What about 700? At 700, it's 1.84, not as good as 900. Let's go back to 800, and at 1.7, 800 seems to be a fairly good approximation of a best fitting straight line. Later we'll find the true value of the slope and the true value of the intercept, but at this point we have, just by looking at where we're putting the red line through the blue dots, come close to minimizing the sum of squared errors.